In this video, I would like to use our double angle formula for cosine to derive one more set of formulas called power reduction formulas. So we know that cosine of 2 theta is cosine squared minus sine squared of theta. Now there's some alternate way to write these because we also have the Pythagorean identity cosine squared plus sine squared equals 1, which can be rearranged in a couple of ways as we've seen in an earlier video. These are alternate versions of the Pythagorean identity. So going back to our double angle formula, I could say, let's make a substitution, and instead of writing cosine squared theta here on the right side, let's replace that with 1 minus sine squared theta. Then we have the following equation. And from here, I can say cosine of 2 theta equals 1 minus 2 sine squared of theta. Let's attempt to solve this for sine squared. So I'm going to add 2 sine squared to both sides of the equation. And I'll get 2 sine squared theta plus cosine of 2 theta equals 1, or 2 sine squared theta equals 1 minus cosine of 2 theta, and then divide by 2, and we get the following identity. Sine squared of theta equals 1 minus cosine of 2 theta over 2. In a similar way, I can go back to my double angle formula, and I can say let cosine of 2 theta equal cosine squared minus 1 minus cosine squared. Here I'm making a substitution for sine squared. Then I have the following relationship. Cosine of 2 theta equals 2 cosine squared theta minus 1. Because in the line above I have cosine squared theta minus 1 minus a negative cosine squared theta. That's the same as adding another cosine squared. If I solve this equation for cosine squared, I will get the following identity. Cosine squared theta equals 1 plus cosine of 2 theta over 2. The reason these are called power reduction formulas is because they allow us to express sine squared and cosine squared in terms of a trigonometric function that does not involve a larger power. It's just a linear trig function, cosine of 2 theta. This becomes very important in calculus as we make substitutions for trig functions in order to evaluate things like derivatives and integrals. I want to show one quick example here of how we can use our double angle formula to rewrite a trig expression. So I want to find a way to express cosine to the 4th of x that does not include any exponents greater than 1. Well, to begin with, I can say cosine to the 4th of x is the same as cosine squared of x squared. And from the double angle formula above, or the power reduction formula above, I have a way to express cosine squared of x. This is equal to 1 plus cosine of 2x over 2. And this is being squared because we have this exponent of 2 on the outside here. Now, what is 1 plus cosine of 2x over 2 squared? If we think through this term by term, we would be multiplying 1 plus cosine of 2x over 2 times 1 plus cosine of 2x over 2. And without showing all the details, we can write this out as 1 plus 2 cosine of 2x plus cosine squared of 2x over 4. Or if we want to write the individual terms, we have 1/4 plus 1/2 of cosine 2x plus 1/4 of cosine squared of 2x. Now, notice that we went from a power of 4 in the original expression to a power of 2 in this expression. However, our goal was to write an expression that does not include any exponents greater than 1. So we need to keep going. The first two terms are fine. We have 1/4 plus 1/2 of cosine 2x. But for the next term, let's once again use the angle reduction formula for cosine squared. This time, theta is equivalent to 2x. So when I replace this cosine squared of 2x, I'm going to write 1 plus cosine of 2 theta, which means 4x, over 2. Or if we write this out, we have 1/4 plus 1/2 cosine of 2x plus 1/8 plus cosine plus 1/8 cosine of 4x. You might combine the two constant terms and say we have 1/4 plus 1/8 here, and that combines as 3/8. So for a simplified expression, I might say 3/8 plus 1/2 cosine of 2x plus 1/8 cosine of 4x. Here is an expression for cosine to the 4th of x that does not involve any larger exponents than 1.